Hello dear students, welcome you all. In this lecture, I am going to discuss about the active filters, right? We know very well that filters play a very important role in electronics. In all electronic components, whether they are used for the purpose of communication, data processing, or in other applications, filters are integral part of that, right? So first of all, we have to understand that what is the role of a filter in electronics, right? Then we have to understand what are the different types of filters and what is an active filter. So if I talk about the filter in electronics, we know filter in electronics is that electronic circuit which is capable of removing undesirable frequencies from the given signal. You recall the working of a half wave rectifier, right, or full wave rectifier. We know very well in case of half wave rectifier and full wave rectifier, the output that we got, that is not a pure DC, but otherwise what should be there, because rectifier is a device that is used for the conversion of AC into DC, right? But the output that we got from half wave rectifier and full wave rectifier, that is never a pure DC, but in fact it is a mixture of AC plus DC, right? It means it contains undesirable frequencies in the output, right? In both the cases, whether it is half wave rectifier or it is full wave rectifier. In full wave rectifier also, whether it is a centrally taped full wave rectifier or it is a bridge rectifier, right? We never get exact DC output. The output that we got, that contains ripples. Ripples means undesirable frequencies, and for removing them we require a filter. We have gone through the passive filters in the previous classes that were used for removing this undesirable AC component from the output of the filter, and those passive filters were dependent on the use of passive components of the electronics, right? So before going further, first of all, look at the active and passive components in electronics. All the components in the electronics can be divided into two categories. One is active components and the second is passive. Now, active components are those components which are capable of doing the amplification. Very simple answer to this question is. And passive components are those components which are not capable of doing the amplification. So you can see here the list: transistor, diode, LED, photodiode, ICs, operational amplifier, all these, right? But resistors, LDR, thermistor, capacitor, inductor, switch, variable resistor, transformer, they are not able to amplify a signal. So these components are known as the passive components. But the component which have the capacity to amplify the given signal, that are active components. So I was saying that the filters that we have discussed in the previous classes, they were passive filters, right? Passive filters means they were dependent totally on the use of passive filters, particularly capacitor and inductor L, right? Inductor L, right? You can recall all those filters. They were simple, shunt capacitor filter, choke capacitor filter, choke filter, then LC filter, right? And then a pi filter. These were the four different filters which has been used by simply making the use of a capacitor and an inductor, right? But no active component is used in them, so that's why we call them as a passive filters. But here in this lecture I am going to talk about the active. Active means now we are adding up an active component in the filter, and active component can be a transistor, it can be an operational amplifier. So here the active filters that we are discussing in this course of masters in physics, we are making the use of a operational amplifier as an active element. That's why we are calling them as active filters, right? Now, active filters also depend upon the functional filtering unit. I mean, the actual process of filtering takes place in a unit that we call as a functional filtering unit, and that functional filtering unit is always either a capacitor or an inductor, right? In passive filters, we were dependent only on these passive components, and in active filters, we are using active component in addition to this, capacitor or inductor circuit, right? So, if I talk about the different active filters that we are going to discuss in this course, then these active filters, they were Butterworth filter, right? This is the most important and commonly used filter, and I'm going to discuss about the different type of Butterworth filters in details in the coming lectures. This filter was invented by British engineer and physicist Stephen Butterworth in 1930. Right. Then we have a Chebyshev filter. Then we have a Bessel filter. Then we have a elliptical filter. So all these are the commonly used filters and a commonly discussed filter that are used in electronics as an active filters, right? But in this course, we will discuss exclusively about the Butterworth filters, right? So now, before going into Butterworth kind of filters, we have to understand that how this filtering takes place, because the actual filtering process takes place in the functional unit, and the functional unit is either a capacitor or an inductor. The role of the active component in this case is that component is operational amplifier. The role of the active component is to boost the signal that is coming from the filter, and maintain its gain, remove the undesired noise. We know operational amplifier have all these properties: reduction in noise, stability in gain, amplification, right? So for this purpose, we are using operational amplifier, right? So now I'm coming to the basic filtering unit that I told you that the basic filtering unit is either a inductor or a capacitor. You can see here, both these are shown here, different types of inductor that are commonly used in electronics. You can see here, right? And these are the different capacitors that are used in electronics. Now, to understand the working of this functional unit means either a capacitor or an inductor or combination of both. Recall the term capacitive or inductive reactance, right? We know very well that the total impedance offered by any material to the flow of electric current is given as Z is equal to R plus iota XC, right? Here R is the real part of the impedance and XC is the imaginary part. Instead of XC, I will write a simple X, right? That will be more, clear. Now, this is the impedance of any material for the flow of electric current or flow of any electric signal. R is real part, X is the imaginary part. We call X as a reactance, right? Now, we know very well that reactance arise because of the two properties of materials. One property is to store charge and the other property is to oppose the flow of electric current or charge through it. The first property, that is to store charge, is the capacitance, and the second property to oppose the flow of electric current through it is inductance. So according to that, we have two type of materials, inductors and capacitors, and they both have inductance and capacitance. So these inductance and capacitance are basically the reactance of the material, right? So if I talk about the reactance of a capacitor, we know very well that the capacitive reactance is equal to 1 upon 2 pi Fc, right? This is the value of capacitive reactance. We write it as Xc. I'm not taking iota here. In some books you can find iota here. So 1 upon 2 pi Fc. Now this is the capacitive reactance. Capacitive reactance means opposition offered by the capacitor to the flow of electric current through it because of the charge storing capacity of this capacitor or this material, right? Now we know very well for AC, F is equal to, it can have any value. If I take the particular case of alternating current in India, then it is 50 hertz. But if I am using any electric signal instead of AC, then that signal can have any value of the frequency. C will be the capacitance of the capacitor. Now, it means this capacitive reactance will depend upon this value of frequency. But if I take the case of DC, then frequency is 0. It means in that case, Xc will become infinite. Now, what is the way? What is the meaning of it? Meaning of it is capacitor is behaving like an open switch for the flow of DC, and it is behaving like a closed switch for the flow of AC. So if I want to block the flow of AC or a particular frequency, what I have to do? I have to connect this capacitor in parallel, right? In that circuit, right? If this is the circuit, in that circuit, I can connect this capacitor in parallel, right? This is the input input terminal of this capacitor, and this is the output. Suppose a signal is coming from here, right? In this way, then when this signal will pass through capacitor, now when the AC try to pass through it, right, its flow is opposed by this capacitor, and this capacitor will offer this much of reactance or simply impedance to the flow of that AC current. But what about DC? For the DC, because this is behaving like an open switch, so DC will pass without an attenuation toward this side, right? So you already have gone through this while you have gone through the shunt capacitor filter in your previous classes. They were passive filters. So this is the working principle of this capacitor, right? If I connect capacitor in parallel, it is going to block the flow of AC or a desired frequency, but it is allowing the passage of DC, right? Now let's look at the inductance. You can see here different type of inductors. We know very well for inductance, the inductive reactance, right? Inductive reactance. Inductive reactance means the opposition offered by this inductor to the flow of current through it. It is XL, and it is equal to 2 pi FL. F is the frequency of the signal, L is the inductance of the inductor. Now, if I am taking the AC, right, we know very well for AC we have some value here. So obviously XL will have some value depending upon the frequency. But if I take DC, for DC XL will be equal to 0 because frequency is 0. It means it is offering no impedance for the flow of DC, but it is offering a very high impedance or impedance for the flow of AC. So if I connect an inductor in series, like this is the circuit, and if I connect an inductor in the series, right, then that inductor is going to block the flow of AC because it is offering the impedance for the flow of AC by this much of amount. But for DC it is offering no impedance, no resistance, so DC will pass without any attenuation. So again the same thing, I have to connect this inductor in a series in that circuit. So these are the two ways of utilizing the property of inductive reactance and capacitive reactance for filtering purpose, right? These are the basic, units, functional units that actually do the filtering, right? But in active filters, in addition to capacitor or inductors, we will make the use of a operational amplifier and obviously some additional circuit components, right? So this is about it. Now, as I told you that in this course, we are going to discuss different type of active filters depending upon their ability to allow our passage of a certain frequency. So you can see here, the four different types are the prominent one which we are going to discuss. The first one is the band pass filter. Second one is, or we call it as a low pass filter. This is low pass filter. This is high pass filter. This is band pass filter. And this is band reject filter. You can see here, what is this graph? This graph is the graph between the gain versus frequency. Gain means ratio of output to input. So you can see in the low pass filter, this is the highest frequency up to which the gain is stable. But if we go beyond this frequency, the gain reduce, very sharply, and this signal will not be able to pass. All the signals toward this side, they will be attenuation band. I mean, they will be blocked by the filter. But all the signals which are toward this side in this pass band range, they will be passed through the filter, right? Now, if you come in the case of high pass filter, then there is a frequency that we call as a lowest frequency, right? F low. If we are coming toward this side, then you can see that the gain is decreasing very rapidly and it is ultimately becoming zero. But if we are toward this side, then the gain is nearly stable. It means all the signals which have frequency greater than this FL, they will be allowed to pass, but all the signals which have frequency less than FL, they are stopped, attenuated, right? So this is the attenuation band, this is the pass band. Similarly, if I combine these two, then I will get a band pass. Band pass means now I have a range of frequency that is allowed to pass, and all the frequencies below this frequency and above this frequency, they are attenuated or stopped. You can see here, FC is the central frequency, FH is the highest frequency, FL is the lowest frequency. Any frequency below FL is attenuated, any frequency above FH is also attenuated, and the gain is stable only in this small region, right? So this is band pass filter, and exactly inverted form of it is a band reject filter. Means all the frequencies between FL and FH, they will be rejected because in this range the gain is very, very low and it is zero at FC, right? But if you are coming to this side, gain is high and stable. Toward this side, again gain is high and stable. So these are the pass bands, right? And this is the stop band, right? So these are the four different type of active filters that we are going to discuss in this course. Although we have one more additional, that is all pass filter, right? All pass filter. All pass filter is going to introduce a phase difference between the input and output signals, but it is not going to block or attenuate any frequency. It will allow the passage of all frequencies, but it is going to induce a phase difference between the different frequency components. So in total, we have 5 different types of active filters that we are going to discuss in this lecture. But remember, in all the active filters, the basic principle is the either capacitance or inductance, or it can be the combination of both, right? As I told you that we can make the use of a simple capacitor, that is a capacitor shunt capacitor filter or shunt filter. We can make the use of a inductor that we call as a choke filter or inductor filter. We can make the component of combination of two that we call as a LC filter, and we can even make the combination of these two, but we will have more than 2 components, then we call that as a pi filter, right? One inductor and 2 capacitors, right? So this is all about the active filters. So in the coming lectures, we will focus particularly on the Butterworth type of filters, and we will start with the Butterworth low pass filter, right? This one, right? So this is all about it. So thank you very much.